Let's wait for 5 to 10 more minutes before we start the session. As usual, your mics have been muted for the sake of the convenience of taking these sessions. In case you want to ask or discuss something, please raise your hand using the meeting option. I'll allow your mic so that you can unmute yourself and speak. In the meanwhile, while we're waiting for other people to join, if you have any doubts from the previous lectures or from the previous solving sessions, then you can ask them. You can raise your hand and ask. I've also pasted the link of the YouTube video of the last week's session in the chat. You can check it out if you have missed those sessions. I've also pasted the link of the presentation slides that I had used in the previous sessions. You can also look at that. Okay, can somebody raise their hand and tell me if I'm audible? Yes, I have allowed your mic, Dr. Satish and M. Sindhu.
Yes, please. You are audible and screen is also visible.
Okay, and when I'm changing the slides, it is also working.
Uh, if you are right now, nothing has been changed. Only
Okay,
the title is shown.
can you check now? Can you tell me now?
Yes, 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 yes.
It is
It's
changing,
okay.
right? Okay, all right.
Yeah.
Okay, thank you, Dr. Satish. All right. Hello, everyone. Welcome to the fourth weekly discussion and doubt clearing session of the NPTEL course, Maintenance and Repair of Concrete Structures, NOC23-CE06, which is taken by Professor Radhakrishna G. Pillai of IIT Madras. I am Ashirvad Satpathy. I am a PMRF research scholar at IIT Delhi. And what I do, I am also the authorized, assigned TA, teaching assistant for this NPTEL course. And what I do is I generally take these weekly sessions where I clear your doubts from the lectures of the previous weeks, lecture sessions that you might have watched from the previous weeks over NPTEL. And we also discuss the assignment problems that you have been given in the previous week, which you have already submitted the answers of, so that you get a better understanding of the subject. There is also another assigned TA of this NPTEL course. His name is Umesh. He usually takes his sessions on Fridays from 7 to 9 p.m. And I take my sessions on Saturdays from 6 to 8 p.m. And before I move ahead in this session, I would also like to mention that the previous week's, as I have already previously mentioned, the previous week's sessions YouTube link has been pasted in the chat, in the meeting chat. You can check it out if you want. And I've also uploaded the slides that I use in these sessions to the Google, to the OneDrive folder, and I have shared the link of that folder, so you can also check that out, and if you can use it if you want. Okay, in today's session, we'll be discussing the week 3 assignment 3 problems. I guess there are around 6 problems, so it is probably going to take not take much time. And this week's lecture was more or less about the deterioration of concrete. In the previous weeks, we had studied the deterioration of steel reinforcement in the concrete, but this was more or less about the deterioration of concrete, the different type of shrinkage, the cracks and creep, and the cracks induced by them, the different kind of attacks, the chemical attacks like sulfate or acid attack, or different kinds of reactions that take place, or different kinds of environmental action that take place inside the concrete that result in the deterioration of concrete. And at the end of this session, we'll also be taking certain doubts that you might be having regarding the week 3 lectures that is related to the deterioration of concrete. All right. This was the first question. Choose the correct option. Statement A: the use of low C3 is cement aids ettringite formation. C3 is calcium aluminate. tricalcium aluminate. So low or which is normally called as aluminate in cement, the aluminate phase. The use of low C3 cement aids ettringite formation during the initial periods of hydration and restricts the availability of monosulfate, thereby reducing the external sulfate attack. This was the statement A. The statement B was the use of calcium aluminate cement in sewer pipelines retard the metabolism of acid producing bacteria and minimize the acid attack in concrete. Which of these statements are correct? The options of both the statements are true. Statement A is true, B is false. A is false, B is true. Both the statements are false. Can somebody answer to this question? Please raise your hand. Please raise your hands if you want to answer to this question. Rutuja, Sindhu, Manisha, Prashad. Anybody wants to try? Dr. Satish, you want to answer?
Yeah.
Okay, go ahead. Dr. Satish?
Yes.
Yes, do you want to answer to this
Statement A
question?
says,
Yeah.
yes. It says that use of low C3A cement means, it means we are talking about sulfate resisting cement. Aids ettringite formation during the initial periods till this available C3A reacts with external sulfates. And after that, since C3A is not available, so formation of tricalcium sulfoaluminate will not take place. So statement A is correct. Now coming to statement B, the use of calcium aluminate cement in sewer pipelines retards the metabolism of acid producing bacteria and minimizes the acid attack. That has been found to be correct. So both these statements are correct.
Okay. Okay. So you want to say that both the statements are true. Yes, thank you. Thank you, Dr. Satish. So before going to the second statement, I want to say something about the statement A. When the C3A content in the cement is low, so what essentially happens during the availability of sulfates, when sulfates are present, the ettringite is stable. And this ettringite to monosulfate conversion uh, is a you know kind of a chemical balance equation. So both the ettringite and the monosulfate phase coexist in the cement pore solution. But depending on the amount of sulfates present in the pore solution, one of these phases more favored. So when the sulfates are more, the ettringite formation is favored, while the monosulfate is less in amount. Now, what happens when you decrease the C3 amount in the cement, when the keeping the sulfate intact, or when the cement is what it is called as a optimally sulfated cement. In case of optimally sulfated cement, and in case of if the C3 content is low, then first when the ettringite is formed, but still there is the C3 content gets exhausted, so all of the C3 reacts with the sulfate and the water and forms ettringite, and still there is sulfate left in the system, then the ettringite will be stable. And since the ettringite will be stable, it will not get converted to monosulfates. And whenever so there is an external sulfate attack at a later age. So since ettringite is already formed, so even if the Cement pore solution is always already saturated with sulfate. So even if more sulfate gets in, it won't react with, it won't have any monosulfates to react with to form a delayed ettringite kind of a thing. So due the lowering the C3A content in the cement will restrict the formation of monosulfates, and therefore the delayed ettringite attack will not take place. So the statement A is correct. And the regarding the statement B, so this is, I have taken a picture from the internet. This is a this is a biogenic sulfuric acid attack. So in case of biogenic sulfuric acid attack, what happens is there are these. So let's say this is a sewer pipe. This is a sewer pipe, and there are several bends in the sewer pipes, right? And when the sewage or the sludge that is flowing through these pipes flows inside these bends, so this area that is totally submerged, the bend that is totally filled with the sewage water, that is having anaerobic conditions. While the area, when it is, I mean, these conditions, when the pipe is not filled totally with water, that has aerobic conditions. Same with this area as well. Now, these under the anaerobic conditions, what happens is the sulfate in this sewage water gets converted to sulfide, and this hydrogen sulfide gets releases into the air, and these thiobacillus thiooxidans are present inside the sewer pipes generally in these kind of conditions. These are the bacteria also known as concretivorous bacteria. And these bacteria, what they do is they, in aerobic conditions, these bacteria facilitate the oxidation of this hydrogen sulfide. So oxidation takes place, and in turn forms this sulfuric acid. And this sulfuric acid can be of the range of 10%. So 10% H2SO4 can be formed. The concentration of the sulfuric acid can be 10%, which will effectively reduce the pH to less than almost 1. 10% sulfuric acid can be formed, and this sulfuric acid will cause the deterioration of the concrete in these portions of the sewer lines. So mostly you can also see this in the lecture slides as well, in the lecture video as well. So the top of these sewer pipes gets affected, the concrete over there gets deteriorated due to the sulfuric acid attack caused by these bacteria, the concretivorous bacteria that I'm talking about. And when you're using CAC cement or calcium aluminate cements, the kind of hydration products that are formed in these cements that are stable in the case of sulfates. When sulfate attack takes place inside the concrete, these hydrated phases are stable, and therefore so there is no deterioration of concrete due to the sulfate attack. And you can see this has been taken from this picture. This is the microstructure of the CAC cement. This has been taken from Gosselin et al. In 2009. And you can see this is a picture of a calcium aluminate cement mortar specimen, which was exposed to MgSO4, which is the magnesium sulfate, that is one of the harshest of the chemicals to cause sulfate attack in concrete, because it leads to brucite formation. Brucite formation. Brucite is MgOH all twice. So this is less soluble in not just the sulfate attack, but again the magnesium also takes part in this reaction in the case of magnesium sulfate attack, and this forms brucite, which is less soluble in water and which will also result in expansive stresses and cracking. But you can see, magnesium sulfate is regarded as one of the most harshest chemicals that cause sulfate attack in concrete. But in the case of using CAC mortar, You can see that when this mortar specimen was exposed to magnesium sulfate for almost 90 years, this is the condition of the concrete over there. So not much deterioration has taken place. So therefore, the answer to this question, so the use of calcium aluminate cement in sewer pipelines can retard the metabolism. So the use of this, since this the concrete in the case of calcium aluminate cement is resistant to sulfate attack, so that will minimize the acid attack in concrete. So the statement A and statement B both are correct. This is the answer. All right. Moving on to the second question, choose the appropriate statements regarding cold weather concreting. Cement with high C3 and C3S content shall be used to increase the early heat of hydration and early strength gain respectively. All right. Concrete made with a high water to cement ratio shall be used to prevent the expansive stresses induced by ice lenses in the case of capillary pores. Sorry. High water to cement ratio is, if it is recommended, concrete should attain a minimum compressive strength of 3.5 MPa, 3.5 megapascals within a few hours of placing. Water curing should be done to prevent the heat loss. Retarder shall be used to decrease the rate of initial strength gain. CSH crystals shall be used as nucleation points for hydration reactions. Which of these statements are appropriate regarding cold weather concreting? Can somebody answer to this question and tell? And let's consider all of these statements one by one. And can you also give the reasons why some of these statements are true and some of them are false?
Let Sindhu or Manisha try. If they don't try, then I will speak out.
All right.
I think they are not forthcoming. In that case, I reply.
Yes, go ahead.
Uh, First option is relating to cement with high C3A and C3S.
Right.
Both will generate lot of heat of hydration initially. So in under cold weather conditions, we require high heat of hydration and early gain of strength. So these products will be useful. So this statement is correct. Now, second one is concrete made with a
Right.
high water cement ratio shall be used to prevent. That is not the correct statement because it's a situation of low temperatures. So this high water content may lead to formation of ice, etc., and may cause deterioration. We want early gain of strength. High water cement ratio is not a good option under this situation. So this is wrong. Now coming, concrete should attain a minimum compressive strength of 3.5 MPa within. So this is the international practice
Right.
everywhere all over the world. In these situations, this is normally specified. So this statement is correct.
Right.
Then uh, water curing should be. I'm not able to see the water curing should be. What is the wording?
Done to prevent heat loss.
No, no, that it is banned under this situation. Water curing uh, is because we want heat generation.
Right.
Water curing is not the best option. Retarders shall be used to decrease. No, in fact, we need accelerators. So this is not the correct statement. And the last one is CSH
Crystals
crystals
shall
shall
be
be
used
used
as
as
nucleation points.
yes. Tests have shown that if you are used as nucleation points, then it helps in these situations. Yes.
Right. Okay. Thank you. Yeah. Okay. Before going ahead to the third statement, I would want to talk something about that. But yeah, the first statement, high C3 and high C3S content are required for to increase the early strength. So early heat of hydration is increased, and that is a indicator that you're gaining the strength early. So in the cold weather conditions, the temperature is very less, and therefore, due to the low temperature, the sorry, there is significant heat loss, and there is no the environment is not conducive for the hydration reactions to take place as it would take place in a normal weather condition, and therefore you would want your cement to have higher aluminate content and higher halite content, so that that will promote the early strength gain and early rise in heat of hydration. So this is a correct statement. Regarding concrete made with a higher water to cement ratio, yes, using a higher water to cement ratio, that will increase the voids, that will increase the void size. But these voids that are increased, the size of these voids are quite large. When using a higher water to cement ratio, these voids are quite large, and therefore that they will not reduce the expansive stresses caused by the ice accretion. So typically so this is the voids that are caused by using a high water to cement ratio. These are known as entrapped voids. I'll go to the next slide, in fact. Yeah. So when you're using a high water to cement ratio, the voids caused are entrapped air voids. And these are typically very high in size, very high in size than the capillary pores. So, so essentially, what happens in case of ice accretion or ice lens formation is that supposedly you have these. This is a sorry. Suppose this is a concrete, and you have certain capillary pores, those that have that is partially filled with water. Now, when the freezing conditions exist, or when the water inside these capillary pores try to freeze, so what essentially happens is they'll increase in size as the volume of ice is higher than that of volume of water, and they will induce cracking in the concrete in the case of capillary pores. And this can be reduced. They can induce cracking in the concrete due to the expansion. But this can be reduced by entrainment of air voids, and these are known as entrained air voids using air entraining admixtures. These are typically slightly higher in size than the capillary pores. So what happens in the case of entrained air voids is that when these capillary pores are present inside the concrete, and there is another entrained air void over here, the water in the partially filled capillary pores, instead of freezing at this in these pores, it gets sucked out into the entrained air voids, which have a larger volume and hence a larger space for the water to freeze over there. And so this is in when the water freezes inside these entrained air voids, it will not create any kinds of expansive trace, and hence there will be no cracking inside the concrete. And when this water melts, in case of thawing cycles, when this water melts, this water again gets sucked back by the capillary pores. Again get sucked back by the capillary pores. So in the case of entered air voids, there is also known as the void spacing factor. So enough air voids, the size of the air void should be comparable to that of the capillary pores, and also the number of voids that should be present inside the concrete should be enough, and the void spacing should be small enough so that the capillary pores have a nearby air voids where the water can escape into. Uh, so this is entrained air voids, and this is different from the entrapped air voids that is caused in the case of water to cement ratio. In case of entrapped air voids, the void size is so large that that will not cause a capillary action, and hence the water will not get sucked out from the capillary pores, because since the pore size is smaller, hence the stresses, the surface tension inside the pores is higher, and therefore the water from the capillary pores will not get sucked out into the entrapped air voids, and therefore it will stay and freeze in the capillary pores, and that will cause cracking. Right? So this is the difference between entrained and entrapped air voids. So this is a wrong statement. Higher water to cement ratio will not give us relief from the expansive stresses caused by the freezing and thawing of concrete. The third one is concrete should attain a minimum compressive strength of 3.5 megapascal within a few hours of placing. And this has been mentioned in a lot of times in the lecture as well. Why the 3.5 megapascal? And I have taken this picture from the Indian Standard 1199-2018 Part 7, which discusses the setting time tests of concrete using the concrete penetrometer, which is also known as the concrete penetrometer tests. And this plot shows the penetration resistance of the concrete versus the elapsed time. So from the point of adding water to the concrete, that the time is calculated, and the penetration resistance that is growing inside the concrete is calculated. Sorry. And you can see that the code assumes that a concrete when the concrete gains a penetration resistance of around 3.5 megapascal, that is that is regarded as the initial setting period of the concrete. The concrete is believed to have set initially, and it has enough green strength so that it will not have any kind of deformation or cracking or anything due to the uh, it has gained enough strength so that it will not have any kind of deformation or cracking due to, let's say, placement or some accidental situation. Again, 27.6 megapascal is the strength that is believed for the concrete to have finally set in this code. So this is just a trivia that I wanted to give you. This is just for knowledge that the 3.5 megapascal comes from the initial setting period of concrete that is believed to occur in the case of the penetration resistance that is gained by the concrete as per the Indian standards. All right, this is a correct statement. So, so this 3.5 megapascal is for the penetration resistance, and so this is also comparable to the compressive strength. So if the minimum compressive strength is this has gained by the concrete within few hours of placement, if it is 3.5 megapascal, then so it will be considered as a good concrete in case of cold weather concreting. Water curing should be done to prevent heat loss. This is a wrong statement, because in case of cold weather concreting, if you're doing water curing, sorry, if you're doing water curing in case of cold weather concreting, what will happen is that the surface water will freeze, and that will cause expansive stresses. The freezing will cause expansive stresses, and that will in fact crack the concrete. So water curing is not done in case of cold weather concreting. Retarders shall be used. This is a wrong statement, because since we are having problems of initial strength grain, therefore retarders cannot be used. In fact, as Dr. Satish also mentioned, sometimes accelerators are used in these kind of situations. And then the last statement was CSH crystals shall be used as nucleation points for hydration reactions. And this is, it's also been discussed in the lecture as well. There are certain chemical admixtures that come as CSH seeds, and these can be used to accelerate the nucleation and hydration reactions. So the correct answers are these three statements. Just give me a moment. Okay. Moving on to the third question. Which of the following statements are true about shrinkage in concrete? The options were plastic settlement or subsidence of concrete is a type of shrinkage. A replacement of cement with SCMs can decrease the plastic shrinkage. Thermal shrinkage is more evident in thick elements compared to thin elements. Good curing can reduce autogenous shrinkage. Good curing can reduce plastic shrinkage. Can somebody answer to this question and also give the reasons why they think some of the statements are true and some of them are not? Yes, Sindhu, Manisha, do you want to try?
I would like
Satish, you want to
to
answer?
answer. Yes, yes.
Go
Uh,
ahead.
First one is plastic settlement or subsidence of concrete is a type of shrinkage. No, this
Okay,
is not a type of shrinkage. It was told clearly in the lecture.
okay.
Replacement of cement with supplementary cementing materials can decrease the plastic shrinkage. Yes, because permeability will be lesser, it will be better and more compact concrete, so it will definitely decrease the plastic shrinkage.
Hmm.
So this is correct statement.
Okay.
Then next one is thermal shrinkage is more evident in thick elements compared to thin elements because lot of thermal gradients will be there within the body of mass concrete. So, so there will be uh, chances of uh, thermal shrinkage, particularly at the bottom of a dam section, etc., where we have larger dimensions.
Right,
Then
right.
good curing can reduce autogenous shrinkage. No, because this autogenous shrinkage flows out of chemical reactions taking place in cement paste. Uh, uh, it will not reduce autogenous shrinkage. And the last one, good curing can reduce plastic shrinkage. Yes, because plastic shrinkage takes place because of evaporation of water. So good curing will supplement the loss, so it will reduce the plastic shrinkage.
Right. Okay. Thank you. Yes. As rightly pointed out by Dr. Satish, plastic settlement is different from plastic shrinkage, and it has been also discussed in the lecture as well. So, plastic settlement is when the bleed water is trying to come out to the concrete surface, and and therefore the aggregates and the rest of the concrete is trying to settle down, and that will create. So so this is, let's say, the surface of the concrete, and these are the rebars. So the bleed water is trying to come to the surface, and that will create a film over the top, while the portion of the surface of the concrete has decreased in height. and so this is known as plastic subsidence, and this is not shrinkage. In fact, the plastic shrinkage occurs in a similar manner, but what happens is when the surface water dries out and it's trying to dry out, and the bleed water is coming to the top, and therefore these the portions between the reinforcement, they have a tendency to subside, they can shrink, while the concrete above, just above the reinforcement, they will not have sufficient amount to go down to shrink as much as the portions between the concrete can shrink, and therefore there will be cracks induced. So I'll just magnify this and draw again. So let's say this is a surface, concrete surface, and these are the reinforcements. So whenever plastic shrinkage is occurring, so these portions between the reinforcement, what they can shrink and sag like this, while the portion above the reinforcements, they won't have sufficient space to go down and shrink, and therefore what will they will do is they will try to travel to the intermediate locations and thereby cause cracking over these reinforcement. This will cause the cracking over this reinforcement. So the aggregates travel to these locations where it can go and accommodate for the shrinkage that is happening, and that will create cracking of these locations because there is expansive stresses over at these locations. So this is typically what happens in plastic shrinkage. So plastic settlement is or subsidence is different from shrinkage, and it is not a type of shrinkage. That is the correct answer. Replacement of SCMs with can decrease the plastic shrinkage. That is true because the finer the materials, that will restrict the bleed water and that will retain water from getting drying out, and therefore it will decrease the shrinkage as well. So that is a true statement. The thermal shrinkage is more evident in thick elements as compared to in thin elements. That is also true because, as discussed in previously in the lecture as well, let's in the case of uh, reinforced earth walls, I'll draw it again over here. In the case of reinforced earth walls, you might have seen that. This has a backfill. This portion has a backfill, and typically the base of these reinforced earth walls is larger in size than that of the top, and this is exposed to air. This side of the wall is exposed to air, and this is a slab on grade, right? And since this is exposed to air, the temperature over here is reduced, while just after concreting, since the element is thicker at this portion, so this will have since this is not exposed to air, and therefore the concrete core would be higher in temperature. The temperature will still be high inside over here, and that will create cracking over at these locations because this has cooled down while this is the concrete at this portion is high in temperature, and that this will have a tensile or expansive stress over here, while this will concrete or shrink, and that will create cracks at these locations, right? I mean, if you look at the front portion of this wall, let's say this is the wall seen from the front, this will have the cracks from the bottom as seen in the case in the lecture as well. So drying shrinkage thermal shrinkage. So this is sorry, thermal shrinkage, because due to the thermal gradient that is caused inside the concrete, the surface is getting cooler, while the concrete that is not exposed to the air, that is hotter in comparison to the surface, that is higher in thick elements. So as seen in this example as well, the thicker portion will develop more cracks, while the thinner portion will more or less have less cracking. So thermal shrinkage is more evident in thick elements as compared to thin elements. This also happens, as we have also seen in mass concreting. So when there is mass concreting construction of dams, or let's say heavy piers, or something of that size, then the core of the concrete is still hot, while the surface of the concrete gets cooler, and that creates the thermal shrinkage, and that induces the shrinkage cracks, the thermal shrinkage induced cracks. So this is a correct statement. Good curing can reduce autogenous shrinkage. No, because autogenous shrinkage is not related to drying or reduction of water. It is not related to drying or transport of water. Rather, it is related to chemical reactions or hydration. So this will the good curing won't reduce the autogenous shrinkage, but curing of concrete elements, like wet curing or ponding of concrete elements inside water, will cause swelling, which I'll discuss in the next slide, and that might compensate for some of the shrinkage that is happening within the concrete due to the hydration. All right, but it can't restrict the or reduce the autogenous shrinkage. But good curing can reduce plastic shrinkage. Yes, as we have also already talked about, plastic shrinkage is more or less related to the drying out of the water from the top, which causes this plastic shrinkage cracks, and therefore having a good having a good relative humidity around the specimen, or curing the specimen or ponding the specimen inside the water, that will reduce the plastic shrinkage. And this is another image I have taken from the PCA document, the Portland Cement Association document, and this compares the shrinkage and the swelling in different types of concrete under different conditions that they are exposed to, and you can see that this concrete that is that is not cured in water, that will have higher shrinkage, while there will be no swelling. But when you're curing the concrete in these cases, when you're curing the concrete in water, that creates some kind of swelling inside the concrete, because the concrete is the pores of this concrete are continuously filled with water, and because water gets sucked out from uh, outside, and that will create swelling inside the concrete, because the size of the voids will kind of expand. Since as we know that the volume of hydrates that are formed inside the concrete is less than the volume of the reactants, that is water and cement, and therefore there will be sufficient space inside the concrete, and whenever we are providing water curing, the concrete swells, and this swelling will compensate for some of the shrinkage that is happening inside the concrete due to the autogenous or the chemical shrinkage. And these two specimens are like compared depending on the type of allowance or the permeability of the concrete. Some of these specimens have been sealed to restrict the drying out of water, while some of these have been exposed to drying. And we can see that in case of the specimens that are exposed to drying, even if we cure the water, that will undergo this drying shrinkage, which will be, of course, less in magnitude than that of those specimens which are not cured in water at all. But there will be some kind of shrinkage. But whenever it was compared with the sealed specimens, like when the concrete elements are not exposed to any kind of drying, the water inside the concrete is intact, and we are also again providing curing water from outside, we can see that the almost all of the shrinkage is getting compensated by the swelling, and therefore at 28 days there is no dimensional, almost no dimensional change in the concrete elements. So this is the effect of water curing on the shrinkage. It due to the swelling, it compensates from some of the plastic or the other shrinkage that is happening inside the concrete. All right. Moving on, so this was the third question, and the answers to this were these three statements. Replacement of SCMs is correct. Thermal shrinkage is more evident in thick elements. Good curing can reduce the plastic shrinkage. Moving on to the fourth question. Assume case 1 and case 2 as shown in the figure. Choose the correct statements from the options given below. The case 1 has a plain concrete slab placed directly on soil or grade. The directly on the soil, and the case 2 has a plain concrete slab again, but it is placed on a well leveled finished soil or grade with a plastic membrane in between. So this is a plastic membrane in between, and the questions were, which of these is correct? So in case 1, plastic shrinkage and plastic shrinkage cracking can occur. In case 2, plastic shrinkage and plastic shrinkage cracking can occur. In case 1, plastic shrinkage cracking cannot occur. In case 2, it cannot occur. In case 1, drying shrinkage cracks can occur after a few weeks or months. In case 2, drying shrinkage cracks can occur after a few weeks or months. Which of these will have, which of these cases will have plastic shrinkage and drying shrinkage, and which of these will not have, and why? Can somebody answer to this question?
Let Manisha or Sindhu try.
All right, Dr. Satish, you can go ahead. If anybody wants to try, I have
Okay,
unmuted, I have allowed their mic so they can unmute themselves and answer or raise their hands. If you want to go ahead, you can answer.
right. In case 1, plastic shrinkage and plastic shrinkage cracking can occur. This is correct because concrete is directly placed on grade.
Okay,
So unevenness is caused. So this is a fit case for plastic shrinkage as well as cracking.
right,
Whereas in second case, concrete is laid on a plastic membrane.
right,
So this is the other situation where whatever is stated in respect of first case, plastic shrinkage and cracking will not take place
right.
because it's a smooth uh, base there.
Hmm.
So these two are correct. Then uh, in case one, we can always this last but one, drying shrinkage cracks can occur after a few weeks or months. Yes, because there's unevenness at the bottom, there'll be some grains, etc. Uh, Situation is right for uh, drying shrinkage cracking after a
Okay,
few weeks or months.
okay.
Right. So three statements are correct.
In case 1, it can happen, right?
Plastic shrinkage, plastic. Yes.
Okay. Okay, these three are right and the others are correct, incorrect. Yes, thank you, Dr. Satish.
Yeah,
Yes, I'll take
yeah.
the help of this another figure from taken from the Portland Cement Association document, and you can see over here. So this is a simulation of a well. Um, this the slab in the first case, you can see that slab is placed on rollers, and it has freedom to move and it has no cracks. And this is a simulation of the case 2 in our case. So when the soil is well graded, the soil is well leveled, and we are providing a plastic membrane. Since the plastic membrane is softer in nature than that of the concrete slab or the soil beneath, therefore it'll take some stresses, and Hence, the subbase or the grade that is providing some kind of a restraint to the concrete will not take place in this when we are using a plastic membrane, because the plastic membrane will capture some of that stress, and hence the slab will be free from these restraint stresses. In the other case, however, this is more or less similar to the case one that we're discussing over here. When the grade or the soil is not leveled well and it is not finished, the surface is not finished well, the these aggregates or the soil can provide sufficient restraint to the slab on grade, and that will since there is restraint, so whenever shrinkage is occurring, that will since there is restraint, so there will be cracking. And this you can see over here that due to this granular fill underneath the concrete surface, there are these cracks are induced because sufficient restraint is provided by the subbase. So this is what happens when so therefore the plastic shrinkage cracking can occur in case one, while it cannot occur in the case of case two. So the first statement is correct, and the second, the case two, plastic shrinkage cannot cracking cannot occur. That statement is correct. Again, related to as also mentioned by Dr. Satish, since it is not properly leveled, so that will create deformations, that will allow for the deformations to occur inside the concrete, and that will promote the plastic shrinkage again. And secondly, the drying shrinkage cracks can occur in the case of case one, because since it is directly in contact with the grate or the soil, so water can transport freely from the concrete to the soil or otherwise, and that will promote the drying of the concrete inside, and that might create drying shrinkage cracks in the concrete. While in the other case, it has a plastic membrane in between, and that will restrict the flow of water. So in the case one, again, drying shrinkage cracks can occur, while in case two, it won't. So these are the correct answers. All right. Moving on to the fifth question, match the columns. Hairline shrinkage cracks, and I'm reading out the type of cracks, and you have to identify which of these actions or which of these deterioration mechanisms can cause these cracks to happen inside concrete. Hairline shrinkage cracks, B is flexural cracks, C is D cracks, D is map cracks, E is popping out of aggregates, F is cracks along the steel reinforcement followed by concrete spalling, G is crack around the coarse aggregates. And the column B, the different kinds of deterioration mechanisms have been listed as follows: ASR or delayed ettringite formation. ASR is alkali silica reaction or delayed ettringite formation. Evaporation of water from the concrete. Cyclic freezing and thawing of water trapped inside the concrete pores. Steel corrosion and formation of ettringite. So which of these from column A matches with column B? Can somebody answer to this question?
I will answer this question.
Yes, go ahead, Doctor.
First, first one is hairline shrinkage cracking.
Yes.
This second option, evaporation of water from concrete. As discussed in previous questions also,
Right.
shrinkage cracking will occur. So A goes well with 2.
Right.
Now, flexural cracks.
Mm-hmm.
These cracks will take place at right angles to the direction of the main reinforcement. So
Right.
no such option has been given.
Right.
So there is nothing to match with anything in column B.
Right.
Now, at C we have D-shaped cracks. So, uh, see D cracks. So here, this is due to freezing and thawing cycles, repeated cycles.
Okay.
It was told in the lecture with photographs, etc.
Mm-hmm.
That since shape is more or less D-like, we call these as uh, D cracks.
Right.
Then D is map crack.
Mm-hmm.
Here uh, we have the first option, alkali silica reaction and delayed attringite formation.
Mm-hmm.
So this goes well with that number of cracks, thus in numbers, uh, uh, something like a map of cracks of
Right.
very small size but scattered. Then E, E means popping out of aggregate.
Aggregates.
So it goes well with three, which is common to D cracks also.
Mm-hmm.
Uh, Cyclic freezing and thawing of water trapped inside the concrete cores. That will cause popping out of aggregates
Right.
also. Then F is cracks along steel reinforcement. That is well established. Those will be linearly along the direction of the main reinforcement. So that goes well with fourth option on the
Mm-hmm.
right side. G cracks around course aggregate. So that is related to attringite formation.
Right.
Like calcium sulfoaluminate is formed and cracks occur around course aggregates.
Right. Okay. Thank you. Thank you, Dr. Satish. Yes, the answer is correctly. He has already mentioned the answer, and this is the correct answer that is given in the options. So I'll go one by one again. Hairline shrinkage cracks, as already discussed, it occurs when evaporation of water occurs in concrete, and that will create these drying shrinkage cracks. Or that drying shrinkage essentially happens after certain hours or after certain days of setting of the concrete. But blasting shrinkage cracks that can occur just after the placement of concrete. That can also occur due to the evaporation of water, and so these hairline shrinkage cracks can appear in the concrete. And you can just do a simple test specimen where you're preparing this initial setting time and final setting time test modes. I have done it in my lab as well. When you're doing this Vickers apparatus tests for setting time of cement, you can see when you're covering the specimens, these or the samples, the setting time samples we are covering from outside, and you're not letting the water to evaporate. And when you compare it with this samples where you're not covering it, you'll see that these hairline cracks appear on the samples that are not covered, and hence the water is getting evaporated. And sometimes we confuse the evaporation of the water for that the cement has already set, but instead it is just evaporation of water, and essentially it is the drying process and not the setting due to the hydration process. So these hairline shrinkage cracks can appear due to the evaporation of water. That is well established. Flexural cracks. So I wanted to draw this picture over here. So flexural cracks, let's say this is a beam. This is a beam element, flexural element, a simply supported beam. And when this is applied with a certain kind of a load, you'll see that the bending occurs. I'll draw a 3D element over here so that you can see. And whenever due to this load, the bending is occurring, the flexural cracks will appear at the bottom fiber, and parallel cracks will appear at the bottom fiber. So these are the flexural cracks. the, these parallel cracks are perpendicular to the direction of the reinforcement, the longitudinal reinforcement, and these cracks appear as the flexural cracks. And there is no mention of these kind of cracks in the column B, and therefore flexural cracks are not a mechanism of deterioration. Rather, they are a structural deformation. The cracks are caused due to the structural deformation in the concrete elements, reinforced concrete elements rather. The D cracks, again, it has been well discussed in the lecture as well. This is due to the cyclic freezing and thawing of water trapped inside the concrete pores. This is the third option. So what essentially happens, there are so when the slabs are cast and there are these joints between the slabs where these joints are saturation points. So whenever these slabs are exposed to the exposed to water or humidity, this is the saturation point, and these joints are generally filled with water. And due to this availability of the water, this water can get inside the concrete elements, and due to the freezing process, it will cause these cracks, and the cracks will appear in the shape of D. So this is away from the saturation points, and this is how it appears. Right? So this is how it appears in the shape of a D. This is the D cracking that is being talked about in the case of freeze thaw resistance, or freeze thaw attack of on the concrete structure. So this is the D cracking in concrete. Then map cracks. Yes, this map cracks occur generally in ASR or DEF, which is alkali silica reaction. So map cracks are generally, they do not follow a certain kind of a pattern, as in the case of flexural cracks or these D cracks that we talked about. These have a certain pattern, but because this happen away from the points, around the points where there is water saturation, and therefore they have a certain pattern of occurring. But in case of ASR or delayed ettringite formation, this is essentially happening at a microstructural level. And so in the case of alkali silica reaction, as you might know, when there is reactive aggregates rich in amorphous silica inside the concrete, and there is presence of alkalis in the concrete core solution, and there is water or sufficient relative humidity inside the concrete, these reactive aggregates take part in a chemical reactions with the alkalis and form a alkali silica gel, right? And this silica gel um, gets entrapped within the porous aggregates and causes expansion inside the concrete, and that will create the cracking of concrete. And these concrete elements, and similarly in the case of delayed ettringite formation as well. So delayed ettringite formation is the formation of ettringite at a later age. So this generally occurs in the case of high temperature curing of concrete, or when the concreting process is carried out at a increased temperature, or in high hot weather conditions. So what essentially happens, above around 70 to 80 degrees Celsius, the formation of ettringite is reduced, or it is minimized. So the ettringite formation is not favorable at that temperature, and therefore, and also the sulfates um, uh, get diffused into the CSH gel that is being formed, and therefore due to the insufficient availability of the sulfates as well, the ettringites is not formed, and monosulfates are formed instead inside the concrete. But when the temperature cools down at a later age, and the sulfates diffuse out of the CSH, and there is a sufficient availability of the sulfates inside the concrete at a later age, these monosulfates get converted. These monosulfates react with these sulfates again and form ettringite instead of monosulfates. And these ettringites have a higher volume, and they create expansive stresses inside the concrete, and that induces cracks of the concrete. And since this is taking place at a microstructural level inside the cement pore solution, there is no defined pattern to these cracks, and therefore these cracks appear like a map kind of a cracking. So this is the kind of cracking that occurs in the case of both ASR and delayed ettringite formation. These kind of cracking occurs. So these are the map cracks. DF or ASR, both of these cases, because these things are happening at a microstructural level. So this can happen wherever there is sufficient amount of cement paste or aggregate present. And we know that cement paste and aggregate are present all throughout the concrete element. Therefore, they do not have a certain definition of the type of or the pattern of the cracks that occur. And this D cracks happens in the case of freeze thaw exposure, right? Popping out of aggregates, again, it happens as we have also seen in the lecture as well. The Due to the uh, high amount of stresses inside the concrete due to the freezing process, these aggregates tend to pop out of the concrete, and this happens essentially in the freeze thaw exposure of concrete. Again, cracking along the steel reinforcement and followed by concrete spalling. We have also again discussed that in the previous lecture. So let's say this is a concrete element and there are reinforcements inside it. And when these reinforcements are corroding and these corrosion products are forming over this reinforcement, they create cracking of the concrete. So this happens along the reinforcement and essentially leads to spalling, leading to spalling. Spalling is the explosive um, falling off of the concrete debris from the concrete specimens, and this is caused in the case of corrosion. So these cracks are formed on the outer surfaces along the steel reinforcement, and they result in the spalling of the concrete. And this is in the case of steel corrosion. And finally, the cracks around the coarse aggregates, that is due to the formation of ettringite, even at a normal age or even at the early age, because these ettringite needles have a higher volume, and when they tend to they get formed, they tend to expand the microstructure of the concrete, and that creates the cracks around these aggregates. And but these cracks due to the normal formation of ettringite, that won't that are very thin or micro cracks, and that won't affect the concrete. I mean the quality or the that won't promote the degradation of concrete. This is a natural process that happens in concrete. So these are the answers to this question. Coming to the last question, uh, the sixth question, that is, consider two mixes A and B, with mix A having an aggregate to cement ratio of 0.8 times that of mix B and a water to cement ratio similar to that of mix B. Choose the right statement about the autogeneous shrinkage in these two mixes, considering all other parameters are same. So the mix A has an aggregate cement ratio that is less or about 0.8 times that of mix B, while the water to cement ratio is same. Which of these statements are correct? Unless water to cement ratio changes, autogeneous shrinkage does not vary among the mixes. Mix B will have lower autogeneous shrinkage than mix A. Mix A will have lower autogeneous shrinkage than mix B. Data is insufficient to comment on the trend of autogeneous shrinkage. Yes?
Yeah, I will respond to that.
Right. Go ahead.
You know, it is stated that mix A has aggregate cement ratio of 0.8 times.
Mm-hmm.
So aggregate content is comparatively lower. So
Mm-hmm.
higher aggregate content means there will be lesser autogenous shrinkage. So first one is incorrect. Uh, Mix B will have lower, yes, because of higher aggregate content relatively as compared to A. Third one is incorrect, and fourth one is also not correct. So mix B will have lower autogenous shrinkage than mix A because of higher aggregate content. That is
Okay.
correct.
Okay. Thank you. Yes, as you have already rightly pointed out. Um, so when the aggregate cement, keeping the water to cement ratio constant, the water to cement ratio is constant, and the aggregate to cement ratio is decreasing. That essentially means that the cement content in mix A is greater than in mix B, right? Since the aggregate content is less in the mixes A and B, the cement content is going to be higher in the case of mix A than in the case of mix B, and all other parameters are keep same. And and this is happening as we know that the cement is the most reactive part in the concrete, and that will take part in so that will contribute to the autogenation and the chemical shrinkage. So essentially, when the cement content is higher in a mix, that will have a higher autogenous shrinkage as compared to a mix that is having a lower water to cement, a lower cement content. So this is correct answer. The mix B will have a lower water autogenous shrinkage than mix A. Again, it has been mentioned that unless water to cement ratio changes, autogenous shrinkage does not vary among mixes. This is not a true statement, because even if the water to cement ratio can be same, uh, let's say a concrete having a cement water to cement ratio, both two concretes having water to cement ratio equals to 0.5, right? But if one concrete has a cement content, concrete A has a cement content of 300 kg per meter cube, and B has a cement content of 500 kg per meter cube, keeping the water to cement ratio same, this will have a water content of 150 kg per meter cube, the mix A, while the mix B will have a water content of 250 kg per meter cube. The water to cement ratio is still same, but since the mix B has a, let's mention this as X and Y, because not to confuse with the mix is given in the question, X and Y. So Y will have a higher shrinkage. So this is not a true statement. The only statement true is mix B will have a lower autogenous shrinkage than mix A, right? All right, thank you. This ends the assignment questions of the assignment 3 of week 3. If you have any questions, you may ask, or else if you have any doubts related to the week 3 lectures, you can also ask them. The session is till 8 p.m. If you
Well
don't have any,
presented, Mr. Satpathy.
thank you, Dr. Suresh.
And in between, I have one piece of information. On 22nd of this month, I was honored by Indian Concrete Institute and number of other professional bodies, Ultratech Cement, with Lifetime Achievement Award in a
Oh,
ceremony here in a prominent hotel. It
oh,
happened on 22nd.
congratulations. Many congratulations to you,
Thank
Dr.
you.
Satish.
And NPTEL had honored me in November. The team came to my institute with NPTEL NPTEL star in one of the
Okay.
categories.
Oh,
Yeah.
okay. Great. Congratulations, Doctor.
Thank, thank you.
Good to know this, that you had these achievements, and again you're continuing to follow a passion and
Yeah.
attending
And
these lectures.
I'm from the field, switch
Right,
over to academics.
right, right. I know, I know.
Okay.
Thank you.
Okay, nice. Well presented. Okay.
Thank you. All right. If you have any questions, you can ask. Otherwise, I'll mute myself for now. The session is till 8 p.m. All right, we are closing the session for today. We'll meet again next Saturday at 6 p.m. Thank you.